Well, good morning. It's almost noontime, but technically it's still in the morning. So good morning. I hope you guys had a relaxing weekend because we're gonna pick things up, right where we left off last week. Good morning. Yeah. So we're gonna go back to basically, set notations. Actually, it's not even basic set theory. It's more like notations. And we're gonna continue the discussion. I'm not starting the lecture yet, so no worries. Um, and what we're going to do is to continue to talk about operators in section 7 because that's something that we did not talk about. So that's where we're going to start today. And one thing that helps when people can kind of get back on a Monday. Wednesday should not be that big of a problem because Monday is only 2 days away from Monday. Wednesday is only 2 days away from Monday. But Monday is technically 4 days from the Wednesday in the previous week. So it is not unusual for people to kind of forget about the notations, the context, concepts, and so on and so forth. So one thing you can do is really just to go to YouTube, not to rewatch the entire thing, just kind of fast forward to maybe the last, I don't know, 10 minutes, 15 minutes, just to kind of recap, where we ended in the previous lecture. That usually helps. It helps me. Sometimes, I forget, what I have talked about in the previous week. So when I prep a class, that's something that I do as well. All right. So we got a good portion of the class, online. I would say about half the class. So that's kind of cool. Yeah, I don't know what you guys do over the weekend, but I watched some really entertaining YouTubes. Yeah, happy Monday. Yeah, one guy was trying to borrow the idea of a Dyson bladeless fan, and he was trying to turn that into a jet engine using the same effect. So that was quite entertaining. The guy was 3D printing all of the components, and obviously when you have combustion, it doesn't work very well with plastic components. But it lasted maybe a second or two. It was roaring. So that was kind of entertaining. We still got about 3 more minutes, so you guys can ask questions if you want to. Alright, so let me check one thing. Give me a second here. Alright, so let me try to take care of this first. I'm being mindful of the time, just to make sure that I don't delay the start of the lecture. Hmm. Alright, we got about a minute to go. Alright, we got about half a minute to go, so I am going to check on someone who is just adding to the class. Alright, so there we go. Got that one done. Cool. Alright. Five seconds. And so screen share on Discord is on. The streaming to YouTube is on as well. So we are ready to go. All right. So I am just gonna go, jump right into the section where we, where we were about to get to last Wednesday. It's about, basically it's not even, I guess you can call these set operators because they do return a value, but for the most part they are just returning a Boolean value for some of them, and then the other ones, they would also return a set. So we'll talk about these, one by one. And once again, for those of you who are trying to take notes and using Joplin or anything that uses Markdown, you can right-click on a formula and then just go to Show Math As, and then go to TEX or Tau Epsilon Chi commands, and this is how you can enter it. You can just copy and paste it, stick this stuff between two dollar signs, and most Markdown engines will recognize this and render it as the math equation. So that's pretty handy. Alright, so the first thing we're going to look into here is the intersection operator. So this is the intersection operator. It looks like a U that is upside down. So A intersecting with B is a set. Okay, in other words, the outcome of this operation is a set on its own. The question is, how do we know the result of this operator is also a set? Now A is a set, B is a set, but how do we know the intersection of A and B is also a set? Just from looking at this equality over here. So this is about notation, right? Because we talked about the notation, how the curly braces or just braces are used to enclose, items inside a set. So the fact that we start with an open brace and we end with a brace here means, the result of this operation is, guess what? A set. Okay, so that's how we know the intersection of two sets is also a set. Next question. What is this notation doing here? Well, this is something that we talked about, guess what? Last week, right? So this is a shorthand, based on what we talked about last time. So in this case, okay, let me see if I can just show both at the same time. Yep, we can indeed. So this is, the p of x is really just a shorthand of some kind of Boolean function, something that returns a true or a false, based on x, and x being, what qualifies as a member of this set. So in this case, when we try to define intersection, every element in the intersection has to meet this requirement. And conversely, anything that meets these two requirements would also be guaranteed to be an element of the intersection of the two sets. So what is the qualification here? Well, the qualification is E has to be a member of A and E has to be a member of B. Now I'm hoping everybody is now getting familiar with the notations, like this little kind of inverted V symbol here is conjunction, which is another fancy word of saying and then this funny looking E symbol here is element of. You can also just kind of abbreviate it as in. So this is E in A has to be a set. So I'm just doing this a little bit to kind of refresh the memory of people. If you guys are saying Tech, we know this already, okay, we got the notations, great, then I'm just being boring. That is okay. On the other hand, if somebody is thinking, I'm not really quite sure what these symbols are representing, or what is this vertical bar doing inside the curly braces, or what curly braces are doing in this particular notation, then I'm gonna say, well, it's time to review the material and get familiarized with all the notations. Okay, take notes. Okay, put all the definitions to one place of your notes so that you can have one single place where it will explain all the notations and all the definitions to you. So that's what I'm going to say. All right, so that's basically, it's the same thing as the next one. In other words, this equality and this definition here, they're basically saying the same thing. Okay, it's both are trying to define the notation of intersection. So in this case, it's saying E is an element of A intersecting with B if and only if E is in A and E is in B. Once again, this operator we talked about in week 1 of this class. Okay, it's one of the 2 additional operators that we added to the ones that you are familiar with. So in addition to not and or, we were also including or adding to it implication and equivalent to. Okay, so this is equivalence, and equivalence is basically implies, but it goes in both directions. All right, so are there any questions about the concept of intersection? And I can give you guys some examples right here. So if you have any questions, conceptual questions about intersection, about how it is defined, go ahead and type in the text channel. If not, I am going to present a few examples just so that you can kind of get some hands-on experience or get some hands-on. I shouldn't say hands-on, that's really not much to do with hands. It's more like mind, right? So this is actually more like minds-on experience or minds-on learning. All right, so let me go find my Vim so I can actually type something. All right, there we go. So I'm going to give you guys a few examples, just so that you can kind of test whether you understand the concepts or not. So we'll start with something that's relatively simple. And I have no idea why it's not showing up. Oh, okay. It died. It died on me. And I have to go find my other window and close that one too, because it just kind of died. There we go. So let me close that too. It does this sometimes. I have no idea why. Obviously, that's a mystery for me to find out later on. But basically, the server would die, occasionally, and causing problems like what we are seeing now. All right, there we go. So I'm just gonna give you a set that has elements A, B, and C. Oh, wrong places. There we go. A, B, and C in one set, and then we're gonna use an intersection. It is called a cap in LaTeX, and then the other one has C, D, and E. And what is the result of that? You can just go ahead and type in the text channel without using LaTeX. Danny has typed in the text channel, so an intersection is also a set. So you could have an intersection of 2 intersections. Yep, you definitely can. But looking just at the example that I have, in the notes here, let me turn off the dark mode. All right. So most of you are right. The people who just type C are the ones that have the notation wrong, because the result of this is a set. So it is important to put braces around the elements that are in that set. So just plain C would actually be considered quote-unquote wrong, okay? Because C is an element, it is not a set. The result of an intersection is a set. Okay, so now for those people who are thinking, but Tech, you're just nitpicking stuff. Well, I'm not nitpicking stuff. This is a conceptual thing, because it indicates whether people understand that the result of an intersection is a set or not. All right. So let's go ahead and take a look at this one here. And instead of C, D, and E, I'm going to have, let's try Z, D, and E, okay? And what would that be? And Chris is correct in the text channel. C does not equal to the set containing C. Those are 2 different concepts. And Danny is correct. Nathan is correct here, because now we have an empty set here. So there's basically nothing in the intersection, but it is still a set. Okay, the intersection of these two sets that do not share any elements is still a set. It's just that it is empty. All right, very good. So we are getting these concepts. All right, cool. And let me give you another one, like this one here. So I'm going to say, A is a set. What is A cap this? All right, so here's the question. I don't even know what members A contains, but I just know that we are trying to intersect A with an empty set. So what will be the end result of this? Nathan is correct. Nathan is correct. Philip is correct as well. So it is not null. It is not null. Okay, it is an empty set. It is also not 0. It is not the set of A. It is just an empty set. There we go. All right. In other words, we cannot find anything that is common as a member to A and the empty set. Now that kind of goes without saying, because nothing is a member of the empty set, not even the empty set itself. Okay, because a set that contains the empty set is not empty. So that's why the intersection of an empty set with anything else is guaranteed to be the empty set. You can also say, well, okay, you cannot say that, but never mind. Never mind. I was thinking about something else. Sorry. All right. So I think we got the intersection concept down, but let me just wait until Dan is done typing. So A intersecting with A would be A. That is correct. Okay, so let's kind of write that down. So it doesn't matter what A is, as long as A is a set. Okay, when you are intersecting a set with itself, it is also guaranteed to be just what you started off with. Yep, that is true as well. Cool. All right. So it looks like we are good here, and we'll move on to the complement of intersection. It's called a union. So union is more intuitive. The symbol representing union is more intuitive because it actually looks like a U, except it's not, actually a U, but it looks like a U. So we're going to use the same kind of definition, and you can see that how these two definitions are very similar to each other. Intersection relies on conjunction, and then union relies on disjunction. That's it. Basically when you talk about A union B, which is a set, we are basically saying, if anything can be found in A or B, then it is an element of A union B, and vice versa. Okay, if anything belongs to A union B, then we should be able to find it in A or in B. Now be careful not to say either or, because either or is exclusive or. This is just a regular or, which means, well, guess what? It can be found in both. We just need an element to be found in at least one of A or B to be counted in as a part of A union B. All right, with that said, let's go through some examples. But first of all, let me see if there are any questions about just the concept itself, just the description of the concept. And if there are no questions about that, then we can go back here and then we can work out a few examples. All right, there doesn't seem to be any questions. So I'm going to do the extremely lazy thing here, and you guys can see how I do it in VI. All right. So in VI, I can say, oh, you cannot see that one because it's at the bottom of the screen. So let me show you the bottom of the screen too, because in VI you can do things, kind of interactively, but you can also enter commands. So I'm gonna enter command here, 1,4, which specifies the range of lines, and then copy to line 5, and there we go. And you go like this, but Tag, you have just replicated everything that we had, and it doesn't seem to make sense. Well, you are right. So we are going to change everything that is cap to cup. So that will change all the intersection into unions. And we can even do something fancy, like everything after the equal sign, because now the answers would all be kind of different. So we can also make some changes over there. We can say from line 6 to line 9, we want to substitute everything starting with the equal symbol and all the way up to the dollar sign, okay, because we don't want to remove the dollar sign. So we want to specify we end at the dollar sign, and we'll replace it with just a single equal symbol followed by the dollar sign, and let's see if that works. Yep, there we go. So I just took out all the answers in after the equality. So now we can start to work on those. All right, so just to show you what VI can do, and potentially why people learn how to use VI, once they decided that computer science is what they are after. Yeah, sure, absolutely. I am probably only using like 2, maybe 2.5% of all that VI has to offer. Yeah, just a tiny little portion, tiny. Line 5 is not rendered properly. So line 5, oh, okay, the one that only has a cup. And that's because I have a space in it. I just put in that space. That's why it's not rendered correctly. The rendering engine, does not like a space right before the closing dollar sign. So every time I start to type in, there's a space, it's gonna go like, oh, I don't know how to interpret this. So that's a kind of like a shortcoming of that engine. So let me just go ahead and do this first, and I'm gonna ask you guys, what am I supposed to include in this case? What is the union between the set that has ABC as its elements and the set that has CDE as its elements? So this is actually going back to check one of the concepts that we learned about set. And Nathan is correct. Very good. All of them is not necessarily a good answer in this case. In other words, if this is actually what I'm asking in an exam and the answer somebody submits is all of them, I will probably classify that as a D grade answer, in an exam. Okay, in this context, in a class, it's not going to be a problem because I can understand from the context. Okay, all of them. The reason why all of them is not a very good answer is, one, it doesn't tell me about the notation, and two, it doesn't tell me whether people are counting C twice or not. Okay, because are we going to say the answer is A, B, C, D, E, where C only appears once, like Nathan, Chandra, and Luke, all typed in the text channel, or are we going to say A, B, C, and then C again, and then D, E? So there are a few questions that will remain unanswered with a specification of all of them. So that's basically why I kind of want to make it clear, because now you guys are starting to understand what I do when I grade in an exam. Alright, so moving on to the next one. No, 1C, as I wrote in the markdown document. There's only 1C because in a set an element can only appear up to once. You cannot have duplicate elements in a set. And that's one of the important concepts that we talked about last week, or week before last. I cannot remember. Probably last week. So if there are two C's, the elements would not be unique, and therefore cannot be a set. It just cannot. It's just that we end up with a syntax error. Okay, we end up with a syntax error because in this class and in many of your other classes in computer science, you'll be only working with a regular set, not a multi-set. I believe in the case of a multi-set, an element can duplicate, but that would be a kind of rare case. Okay, it's not common that people refer to a multi-set, but in almost every single context in computer science, we only refer to the regular, kind of set where an element cannot be duplicated. Alrighty. Alright, so the next one is, let's check out what is in it. So I'm pretty sure with this one, all of you now know that we have A, B, C, D, E, and then Z. And then somebody is going to complain, go like, but Z should go before D. Well, ordering does not matter either in a set. So A, B, C, D, E, Z is really exactly the same set as Z, A, B, C, D, E, or A, B, Z, D, E, and so on and so forth. Because ordering has no meaning inside a set, unlike a vector or an array. Like files, okay, like file of one particular name can only appear once in a folder. Yeah, we use the folder example quite a bit. All right, so getting to the next one. Okay, so we have A union with an empty set, and the only thing we know is A is a set. What is the answer to that question? Yep, you guys are all correct. There we go. It's just A. And obviously the last one is also just A by itself. Excellent. So I think we are getting the concepts of intersection and also union. And I'm just going to pause here to see if there are any questions regarding these two operators. And if there are, we'll address those before we move on to the next operator. Alright, so I don't see any questions, and we're going to move on. So the next one is kind of interesting because we are borrowing, this is the next one, is a difference. Okay, so we are looking at the difference between two sets. So when you look at the definition, A, you can call this minus B, if you want to, because it is borrowing the subtraction symbol from arithmetics. So A minus B, or the difference between A and B, it looks like intersection, doesn't it? Because it uses conjunction. Except we want E not to be in B. So it includes everything that is in A, but not in B. So the difference between A and B would consist of things that are in A but not in B. And at the same time, if you can find something that is in A and not in B, that thing is also guaranteed to be in the difference between A and B. So let's take a look at these operations that we have already looked at. And we're going to have to include one more example in this case, but we'll go ahead and copy line 6 to line 9 to the end, which is line 10. Oh, okay, that didn't work. It says incorrect range. So let's try again. So line 6 to line 9, copy to line 9. There we go. Alright, so now we're going to take a look at subtraction. So we are going to change all the cups to subtraction. So substitute all the cup with a minus symbol. And I think that's all we have here. There we go. Excellent. And then we also want to get rid of all the answers. So line 10 to line 13. Substitute equals to all the way to the dollar sign with equal to and then just the dollar sign. And there we go. We got rid of all the answers. So now we can work with this. Alright, so the first one first. What is the difference between the set A, B, C and the set C, D, and E? It will be A and B only. That is correct because the element C is shared between the two, and we only want to count in elements that are in A, which is this one here, but not in B. Since C is also in B, we cannot count that in as a part of the result. So you guys got it right. Excellent. So I'm going to put in here. There we go. And what about the next one? The set A, B, and C, the difference between the set A, B, and C versus the set Z, D, and E. It will just be A, B, and C because they do not share anything. So if these two do not share anything, then the entire set from the left-hand side is the answer to the question. Excellent. Pointer notation. Oh. I wonder what a dangling pointer would look like. Maybe an amputated finger with blood gushing out. That is still a valid pointer. It is it's almost like a null pointer. Can we use this notation on exams? I think Chris is basically saying, in the answer to one question, person A would say, please refer to the answer area of person B of the same question. I'm going to allow that because you guys are guaranteed to get different questions in the exam. So referencing, to another person's answer is guaranteed to get a 0 in the exams. Yes, evil laughter. That's exactly what it is. All right, next question. A is a set, so we don't know what is in A, but what is the difference between A and the empty set in this case? So we don't even know what is in A, so how can we answer that question? All right, you guys are getting this. Excellent. What about this one, the last one? Okay, we are trying to look into the difference between A, and it sort of makes sense, right? That it is going to be an empty set because everything in A is in A. Very good. All right, so we are getting all of these concepts. Cool. Very cool. Yeah, I was about to give you guys an extra one, which is ABC minus ABC, but this one covers that one already. If A is a set, not knowing what is in A, what is A minus A? It's the empty set. So I got that one covered already. Excellent. Alright, so what is next? The next one is actually a little bit harder to understand because it involves the addition of a new notation. So this time, I'm going to remind you guys it is important to read ahead of time. Because if you did, then it would just be kind of like, okay, let me just listen to text explanation and kind of make sure that my understanding from reading this material is correct. As opposed to, I didn't read this material at all. This is the first time I'm looking at this notation here. Then there's nothing to check against, right? Because you don't start with an understanding of your own to check against my explanation and the examples. So once again, I'm just preaching and nagging here. Okay, this is what dads do, or some dads do, is to nag, right? Keep nagging. It's like, okay, you guys need to read ahead of time. It is going to be beneficial. And then the bottom line is, it really is not my grade. I hate to put it that way because some people would go like, you don't care about my grade. I do, and that's why I keep reminding. Yeah. Alright, so getting back to the main material over here. This is called the Cartesian product. Okay, this is the Cartesian product operator, and it defines something that looks a little bit funny, compared to what we have seen. And some people look at this and go like, oh, that's just intersection. We talked about intersection. How hard can this be? Well, each element is no longer just one thing. Each element is in this particular form. And in this particular form, the parentheses are significant. Okay, it has meanings. So when we use parentheses like these, we are making what we call a tuple. Okay, a tuple is kind of like an array or a list. Okay, depending on the programming language. Some programming languages would use square brackets to enclose things in an array. JavaScript would do that. Some other languages, maybe Perl, okay, would use parentheses to surround things in an array. So you're basically creating a literal array in this context. But basically, xy here is forming an array of two elements. The first element of the array is named x, and x has to come from A. The second element is named y, and y has to come from B. So this is not intersection in any way. Okay, this is actually creating two tuples. Now the term two, as in the numerical value 2, and then followed by tuple, basically means we are having tuples that only has two elements. From your perspective, knowing your programming concepts and all, you can look at a tuple as an array. Okay, so every time I say tuple, you can think array, tuple, array, tuple, array. Okay, so but in this class, I'm going to stick with the term tuple, because that's how a lot of these concepts are introduced. All right, multiplication table is a Cartesian product. Not exactly. Not exactly, because each cell in the multiplication table is not just the one element from the left-hand side of the operator and one element from the right-hand side of the operator, because in the multiplication table you actually have the product as the value of each cell. So I would say the concept is similar but not exactly the same. Chess notation. Yeah, I would say chess notation is a Cartesian product, but I'm gonna give you guys an example, because this one does require maybe a few examples to illustrate. So I'm gonna start with something that's relatively simple. Okay, so I have A, B as one set, and then we'll say times. This is how you make the Cartesian product symbol in LaTeX. It doesn't appear as a cross yet, because I have not ended the dollar sign on the other side. I even have not started it yet. All right, so AB times, let's make this kind of really easy to understand. Okay, so one set has AB as its elements, the other set has 1, 2 as its elements. So the result of this is also a set. Okay, not really surprising here. The question is, what is in that set? Okay, so I'm gonna get back to this, and I'm just going to put some question marks over here so that we know this is where we left off, because my watch just buzzed me. It's time to take row. Yay, it's row taking time. And Nathan is correct about the answer. And Eric is missing a few things. Alright, so let me get back to home and get out of student view. Yeah, getting out of student view means there's a lot of distraction, because I got lots of stuff here that is not visible. And here's your row taking activity, and I was about to say unhid it, but I've just made it visible. But let me go check the answer first. So don't type anything yet. Let me go check the answer first. I just looked at it this morning, but sometimes I just forget. It's just union, U-N-I-O-N, lowercase. Just copy and paste from the text channel. It's already open to you guys, so you don't have to wait. I was just displaying this to make sure. And you have until 12:45 to do it, and it's not even 34 yet. You have what, 11 minutes plus to enter the word union. And if anyone at this point is asking, but why did you choose the word union, I'm gonna say roll back the lecture by about 20 minutes and you'll find out. And that's one really cool thing about live streaming in YouTube is you can actually do that. You can basically go to the YouTube live stream and then use the bar, the little scroll bar thing, the thumbnail thing, and actually roll back, by like 20 minutes or whatever amount of time you want to, and then just kind of repeat that section. So it's kind of cool that way. Yep. So plenty of time there, but time is a real number, so it's not going to be a discrete thing that we talk about in this class. Exactly, and then miss the live content. Well, that's why I'm kind of chit-chatting a little bit here, just to give people the time to kind of answer the activity, but looks like most people are done with it already. So now we can kind of return to our regularly scheduled program, as they say on TV. I don't watch TV anymore, but when I watched TV, like many years ago, that's what they say sometimes. All right, so getting back to the example, which is here, and the answer from, I'm just going back to the text channel. So the answer from Nathan is correct, okay, because we are basically pairing elements of A with every element of B, and then that's basically what we're doing. It's kind of like a cross product. So we have A1 as one element, A2 as another element, B1 as an element, and then B2 as another element. Alright, so I'm going to pause here and see if there are any questions about the concept of a Cartesian product. Alright. Well, there's MacGyver and then there's MacGyver. There's, Dean Anderson as MacGyver, and then there's the new guy, I don't know his name, as MacGyver. And trust me, nobody beats Dean Anderson, especially in SG1. Stargate SG1. No. The short answer is no. So the answer is no to Daria. Do not try to shorten the notation. Always put in the parentheses and the commas. Yeah, I think they have done Stargates to death already. So I'm not really sure what more can they do with Stargates. We have stationary Stargates. We have mobile Stargates. Alright, so ordering does matter in a tuple because it is an array. So the tuple A1 is considered different from the tuple 1. A1 is different from 1A. So ordering does matter. Let me just kind of type, in Markdown. So A1 as a 2 tuple does not equal to 1A as a 2 tuple. Those two are different. And why is it not liking my notation? Oh, okay, I don't need backslash here, because they're just regular parentheses. There we go. It's NE. NEQ may work too. Let me try that. Oh, okay, so they are synonymous. Okay, I did not know that NE and NEQ are the same. I've only used NE before. So, all right. So let me go check the text channel. It is not a 2D array. Okay, you can sort of look at it as a 2D array if you choose to. Okay, let me give you an analogy here. You have a bag of marbles, okay? So the marbles are labeled, A1, A2, B1, B2. Now, if you want to just kind of look at the marbles in a bag, like, oh, okay, it's just a collection of marbles, where there's no inherent structure, no inherent ordering and whatnot, that is the concept of a set. Now, on the other hand, if you want to say, but I like things that are structured, so when I take these marbles out, I want to line them up into a 2x2 grid, that is okay if you want to visualize it that way, but there's no implicit structure in a set. Okay, so I just want to emphasize there's no implicit structure nor ordering of elements inside a set. Now, if you notice some patterns about the elements and go like, oh, sometimes I want to look at it this way and just kind of line things up this way, that's perfectly okay. But that is not inherent to items being in elements in a set. Yep. All right. Oh, tuples are definitely not sets, okay? Because tuples, you can have tuples like this, okay? Oh, not here. So you can definitely have duplicate items in a tuple, and 1A 1 2 1A is a valid tuple. Now, it doesn't quite belong to the Cartesian product that we are talking about, but it is a valid tuple. It's a valid 5 tuple because it's a tuple that has 5 things in it. All right, so yes, Chris is correct. Okay, A1, using the set notation does equal to 1A using the set notation, but when you use round parentheses, they are no longer the same. Exactly. XY graph coordinates are examples of tuples. Yes, that is the case. In fact, later on we'll do some really kind of fun stuff with 2-dimensional coordinates, and then 3-dimensional, and then 4-dimensional, and so on and so forth. Eric says, so ordering matters for sets, but there's no inherent way of ordering them. Nope, ordering does not matter for sets. There's no inherent ordering whatsoever for elements that are contained within a set. There's no ordering within a set, but ordering is significant within a tuple. A tuple is an array. So remember, a tuple is an array and a set is not an array. Ordering does not matter in the case of a set. Alright, would 3D graph coordinates be examples of tuples? It can be seen that way because you have 3 components, and ordering does matter, right? Because the coordinate of 1, 2, and 3 is definitely not the same place as 3, 2, and 1 as tuples, as 3D coordinates. Yep, that is correct. Alrighty. Are there any questions? Alright, so I'm going to give you guys one more example, as in, okay, let's check, whether we understand the notations or not, okay? So I'm going to start with, 2, 1 as a tuple, and I'm going to use the in operator here, and then we're just going to copy, the one that we had earlier, which is AB times Cartesian product with 1, 2, and I'm going to put an equal sign all the way back here, and I'm going to put an overall parentheses around the entire thing, and then I want you to answer this question. What is it? Exactly. All right, very good job. Okay, because this question is really asking, is it true or false that 2, 1 as a 2 tuple is it in the Cartesian product of A, B, and 1, 2? So the answer is false here. That is correct. Okay, that is awfully confusing because a check mark because that cross can be seen as a check box that is checked, which is positively saying yes. It can also be interpreted as a cross as in no. So it is very confusing, and if I see answers that are confusing in an exam, I'm just going to say I have no idea what the answer is, and I would just not give a point in those cases. So it is a good thing that you guys are trying all. You guys are just pressing all the buttons, right? In an airplane, and it's okay to do that when the airplane is on the ground and there's no fuel in the fuel tank and the electronics are all turned off. Go ahead and punch the buttons. But when we are in flight in an exam and people punch those buttons, something's going to go down. But you can punch those buttons now. So let's not use alternative notation. Let's stick with what we know and what TAC has been using in class. So if you say, but I want to answer the questions in my own language, it's not even a specific, particular to a culture or a country. This is my internal language in my head, and I want to answer all of these questions in my internal language. When I grade the exam, I'm going to say I do not see any evidence of any understanding of the material, because I can only use the language that we have been using in class as the interpretation. So there you go. Yep, true, false is the right kind of answers. Yep. Circle is yes, cross is no. It all depends on in what context. I'm laughing because sometimes I go to these shooting matches. So in those matches, you have what they probably call a scorecard, and on the scorecard, it is exactly opposite to what Nathan is talking about. If a target is hit, we put a cross. If it is a miss, we put a circle. I just have to laugh, just because when we start to deviate from the notations that we have been using, in this class, that we know, okay, this means true, this means false, and so on. Everything else can be ambiguous, and the interpretation can be exactly the opposite to what you think it is. So there we go. Yeah. All right. So it's good that we have this little conversation about notations, just so that people do not try something new and fresh and interesting and innovative in an exam. Yeah. So don't do that. It may not be good for your grade. All right. So let's see what else. I think we got a few more things here. Okay. Subset of. Oh yeah, we got subset of and proper subset of. So let's go ahead and take a look. So yeah, sure. So let's go ahead and do some kind of funky ones. I like funky examples. All right. Yeah, absolutely. So we're gonna do one that's kind of funky. Well, we'll do a few that are funky. So we have a Cartesian product with a, and that's it. Okay, you go like, whoa, what is this? They are the same. The left hand side and the right hand side are the same. What is the answer? Oh, Nathan has got it. Yep, that would be the answer, and that would be the only right answer. So if anyone gives me in parentheses just one a, that's wrong. If someone gives me, a comma a without the parentheses but inside curly braces, that would be wrong. If someone gives me, I don't know, just the parentheses a and then close parentheses but without the braces, that would be wrong. Yes, this is the only way to express the correct answer. It is a set that has a single element, and that one single element is a two tuple. Both elements of the two tuples are a's. That's how picky I'm going to be when I'm going to grade. Yep, that's right. And the answer of a squared is wrong as well. I think you guys are just testing me, right? You guys are all tracking a wrong counter, like in certain movies, people keep track of a body count. So you guys are just tracking a wrong counter. It's like how many times can tag say wrong in a single class? And I really don't mind people doing that at all. Count all you want. Because wrong, guess what? It's just wrong. Yeah, Mondays are any day. Any day is a good day for memes. That's a personality type kind of thing. I suppose if you look at the W sideways, the W does look like your two uppercase L's. Alright, so one is done. Let's try another one. Okay, so let's try. You know, that picture reminds me of The Hunt for Red October. It's a really old movie. You know, Sean Connery was still kind of he's not young in that movie, but he's still kind of really commanding and stuff like that. And that hand reminds me of when James Earl Jones. That's it. When James Earl Jones, on I think it's a destroyer, pressed the button of a torpedo self-destruction. And then the camera panned up to his face, and then he just, in his kind of very unique way of half smiling but not really smiling way, and he said, "I was never here." That was one of the favorite moments of that movie. Actually, it's like, wow, now that's James Earl Jones. Nobody else can do that. Oh, all right. And from what I know, the song that the Russians sung in their submarine was all just gibberish. And if anyone in this class knows Russian, they can comment on that one. It's like, oh yeah, that's all gibberish. They're definitely not singing anything in Russian. Anyway, let's look at this example here. Okay, we have a set of A, Cartesian product with a set of nothing. It's an empty set. So what would be the result of this? And once again, Nathan has gotten it, and so has Mohammed. Alright, good job. That is the correct answer. It is an empty set. Because there's no way to make a two-tuple. Because the requirement is, every element of the result of a Cartesian product, one element has to come from one set, and then the other element has to come from the other set. One from the left-hand side, one from the right-hand side. Now, since one of these two sets is empty, it becomes impossible to make a two-tuple because one of the two sets cannot contribute a member to form a two-tuple. That's why the Cartesian product in this case is an empty set. Yeah, I know. It's because I broke I broke the ground wire somewhere within the cable. I cannot find out exactly where to fix it, so we just have to kind of bear with the ground loop for a while until I cut the cable and keep chopping it until I find the breakage. All right. That is correct. So Luke is correct. If you are making a Cartesian product between A and 1, 2, you end up with A1, A2. That is correct. Not the empty set. Yep. It's not that easy. The cable is actually kind of hardwired, to the mic. So I'm gonna have to open up a lot of things to fix it. But I can cut it. It's easy to cut it and then reattach the this is using the those really gigantic 3-pin header for professional mics, so I can always resolder that. I know how to do the soldering part, but I cannot find where the open circuit is very easily. There you go. Alright, so looks like we got the concept of Cartesian products. Any questions about finding the Cartesian products of two things. Yep, exactly. It is. It has a XLR connector, and then it goes into an amplifier. It goes to. I can show you guys. I mean, let me see if I can. Yeah, I can do that. It has. It connects to this particular thing. I hope Homeland Security is not paying attention. Because it connects to a kind of high gain amplifier, because the mic itself has very limited signal, and that's kind of by design. So the signal has to be amplified before it goes into the other thingy, which takes a XLR connector from a mic, and then it connects through USB to the laptop computer. So it's a yeah, the FBI has joined the server. I was watching Born Ultimatum, I think, and so when someone mentioned Black Briar, over the phone, the CIA instantly get the notifications like, oh, somebody mentioned this code name. But all things considered, it really is a pretty good amplifier. Very low noise floor by itself. Gets the job done, so I cannot complain. All right. Oh, okay, that's cool. That is cool. All right, so we got Cartesian products, and now we are moving on to the next one, which is a subset of. Okay, so this symbol here that looks like a C with a bar underneath, that's subset of. So now we are talking about A is a subset of B, and I'm getting so lazy that I'm using if and only if the difference between A and B is an empty set. Now there's another way to express it. Okay, so I'm going to give you the other way to express this, and then we're going to get back to this particular definition. So let me go back to the markdown notation thing, and then this time we'll define A is a subset EQ of B is a set. Okay, so the question is, what is in that set? So in that set we have element E, so every element in this particular set has to meet all of these requirements, and conversely everything that meets these requirements have to be an element of, oh, I take it back, never mind. That was me, just not thinking out straight. Alright, so a subset of a subset of is basically saying everything in A is also found in B. So it is not going to give you a set. Okay, this particular operator does not return a set. It returns a Boolean. So it's either true or false. Okay, so if it is either true or false, then how are we going to express that, right? Do we have any more foundational notation to express this, right? We're going to have to use quantifiers. Okay, so if we want to actually use this using notations that we have already introduced, and quantifiers are already introduced because I accidentally introduced quantifiers thinking that I was done with all the set notations. Remember that? So we actually kind of we can cheat a little bit here because we already know about quantifiers. So I'm going to use quantifiers to express this now. Okay, so we're going to start with a for all. So we're going to say for all element E in A, E is also in B. So that's one way to look at this. A is a subset of B is exactly saying the same thing as everything in A is also in B. Alright, so Nathan says, can we also express it as there doesn't exist an x such that x is in A and x is not in B? Yes. Okay, very good. Okay, let's go for that one. Okay, so let's go for that one. And so now we are using negation and then exist, right? So we have a negation here, negation, and then instead of for all, we can say exists. And so that does not exist an x such that x is in A but not in B. In A but not in B. So we can put a negation here too. Yep, so these two are basically saying exactly the same thing. Because what we can do is we can distribute this negation all the way to inside the qualifying condition. But remember, if we want to do something like that, now this is from the quantifier discussion, is if you want to move the negation of the quantification itself, which is referring to exactly just this negation, to inside the qualification, you can do that, but by doing so, you also have to change the quantification from an existential to a universal, or vice versa. So if you start off with a universal, you have to change it to existential. And once you move this negation to the inside, then you end up with double negation, which basically means they cancel out and we get this notation back again. So Nathan is correct. Okay, the other way to look at this is to say you cannot have an element that is in A that is not in B. Yep, so that is correct. Alrighty. But we have seen something like this before, haven't we? Okay, we have seen something like this, and the way we encountered something like this was the difference. So when I say A minus B equals to an empty set, it really means exactly the same thing. There's nothing in A that is not in B. Everything in A can also be found in B. That's basically what this part is saying, but that's also how we can define that A is a subset of B. So there we go. Are we good so far with this, or do you guys want some examples of subset of? Subset of is actually a little bit easier to understand compared to the other ones. And let's go ahead and check that out. Uh-huh. In the notes? Okay. Uh-huh. Go ahead. Oh, okay. The one that we used today in class. There we go. This one? Mm-hmm. Mm-hmm. Okay, so this notation is a shorthand. This is basically a filter. So let me go back to the discussion that mentions this, because we did talk about this notation. It's a filtering shorthand of how to use quantification, because quantification by itself is always applying to everything in the universe, which is not exactly very helpful. So we use a filtering notation to basically say, okay, let's not talk about everything in the universe. Let's talk about just things in A in this case. So yeah. Yeah, so this is, yeah, sure, absolutely. And then we got the question. Eric asked a question. Does that mean empty set is a subset of every set? And that is correct. Okay, so it doesn't matter which way you look at it. You can look at it this way, or you can look at it using the definition in the module. It works in both cases. Now let's check out how that works, right? So if you use this notation and A turns out to be an empty set, and you're asking what is in an what is in an empty set but not in the other set? The answer is nothing, right? Because the empty set has nothing. So this equality is always true if A is an empty set to begin with. So that means if A is an empty set, it is always a subset of whatever other set we are talking about, including the empty set itself. In other words, the empty set is a subset of itself. Okay, that's perfectly okay. It's not a problem. Now, if we use the notation that we talked about today, using the universal quantifier, the first one, then it is always true as well. Okay, because if A is an empty set, then we cannot find an element that belongs to A, which means by default the universally quantified statement is true, because there's nothing that this B in B can be applied to. So when you have nothing to apply the criterion to, then the universally quantified statement or expression is automatically true. Now the question is, but where did we say that? Where did we mention something like that? It was from the previous class. I gave you guys the code in JavaScript where the return value was initialized to true when we're dealing with a universally quantified expression. So that's how we tie in all of these things. Okay, I know that I only mentioned it once, but that's why you guys need to study. So that when I mention it once, you look at it again and you absorb it, and then you go back to it and then look at it again and make sure that you kind of understand what the concept is about, what the notations is trying to express. All right, very good. So very good. So Eric made a very good observation that the empty set is indeed a subset of every set, including the empty set itself. So that's very good. And then what we're going to do next is to look at the other notation that is very similar to subset of, except it doesn't have a bar under, like right here. So this is basically saying A is a proper subset of B. Okay. So now the question is, what does it mean when A is a proper subset of B? And once again, I'm getting really lazy just by using notations that we have been introduced already. So in order for A to be a proper subset of B, A has to be a subset of B first. But on top of that, we need one more extra requirement, is B minus A has to be non-empty. So there has to be something in B that is not in A. So if both of these conditions are satisfied, this is conjunction, right? This is AND. So when both of these conditions are satisfied, then we can claim that A is a proper subset of B. All right, so Nathan is typing something in the text channel, and you guys can kind of think about this a little bit before we still got about 10 minutes before the end of class today, so we can take some time to kind of let all of this stuff sink in. All right, so Nathan just typed, the empty set is a subset of the empty set is true, and to say that the empty set is a proper subset of the empty set is false. That is correct. Does that mean non-proper sunsets are equal? I don't understand anything about equality between sunsets. Yes, subsets. Okay, that we can talk about. So does that mean non-proper subsets are equal? They can be equal, they don't have to be. Okay, so let's go ahead and use a few examples to illustrate that concept. Okay, so I'm going to use all right, so we'll go ahead and use the empty set. Okay, and subset EQ something that is non-empty. Okay, like that. This is true. Okay, and then we'll say, what about the empty set versus the empty set itself? That is true as well. And then we have A on this side. This is false. And then a set is its own subset is also true. Oh, okay, the R is not supposed to be here. There we go. So there we go. And indeed, we can say if we know A is a set, A is a subset of itself is guaranteed to be true. Okay? Yeah. All right. So now, on the other hand, if I just remove the EQ part, which means proper, then it doesn't matter what set we are talking about. The set being a proper subset of itself is guaranteed to be false because they have exactly the same elements, which means the set on the right-hand side of the operator cannot possibly have elements that cannot be found in the set on the left-hand side of the operator. So that's why if you are just saying, oh, I just have a set, A is a proper subset of itself, the answer is guaranteed false. It cannot possibly be the case. So are we good so far? Are we kind of getting the differentiation between the concept of just subset of versus the concept of proper subset of? Maybe. All right. So assuming there are no questions about the concept of subset versus proper subset, we oh, okay, there we go. Okay, we got a few confirmations. Thank you. All right. Third last. I'm not really sure what third last is referring to. Relative positioning only works if you also tell people to what you're referring to. Oh, previous screen. I see. Okay, third to the last like this one. What about it? Oh, it is true. Sorry. Yeah. There we go. Thank you. So Mohammed caught it, okay? Because I was wrong when I say the set that has A in it is a subset of a set that has A in it is false. It is actually true. It's always true in that case. Very good. Thank you. Thank you. All right. So I think we are ready to move on to the very last operator. It's kind of an operator, All right, many times we are interested in the number of elements in a set X, and the notation is just bar X bar. So, so in this case, we are not looking at quote unquote the absolute value. It doesn't make sense to look at the absolute value of a set. There's no such thing. So instead, I'm using the bar notation to mean cardinality. Okay, so technically this is called the cardinality. But if you want to look at it kind of loosely, you can look at it as the number of elements in a set. Okay. Now, why don't we just say it's the number of elements in a set? Why do we use this kind of fancy word of cardinality? Well, I can give you one example of why. What about the cardinality of the set of all integers? They go like, it's infinity? Well, infinity is not a number. Right? So, and then if I ask you, how do we compare the cardinality of the set of integers versus the cardinality of the set of all the real numbers? Then most people would go like, well, I guess they are the same because one has an infinite number of elements and so does the other one. So you can consider them the same? And the answer is no, they are not the same. Even though they are both quote unquote infinity, you can still compare them. So that's why cardinality does not necessarily mean exactly the same thing as the number of elements in the set. Now, if your set has a finite number of elements, then yes, they're really the same thing. But when you're dealing with a set where the number of elements is infinite, then you got to be careful. Okay, so we're going to deal with that specific problem in, I would say, maybe in a week or so. After we talk about functions, we'll talk about that. All right, so we got a few examples in the text channel. The first one is correct, so Elijah is correct. The cardinality of the set that has A1, A2 as two tuples in it is 2. That's good. And then the other one is the the cardinality of the Cartesian product between ABC and 1, 2, 3 is 3 to the power of 2, and that is correct as well. Well, since we are on this topic, let me ask you this question. Now, this is really a consider this a ungraded assignment. Okay, in other words, it will be kind of interesting to think about it. Because as you think about this particular question, you will be thinking about these concepts. So we are using cardinality, and let me just put all of these in. So I'm looking at the cardinality. And I'm looking at the cardinality of a set, right? No, I'm not talking about the empty set, okay? That's just 0, okay? Because there's nothing in the empty set, so this would not be a very useful thing to do. So instead, I'm asking you, each element is x in this particular set, and x is a subset eq of, I don't know. We'll just make it a very simple one this time. We'll just say A, B, and C. There we go. All right. And what is the answer to this question? All right. So I'm not asking you guys to do this like right away. Some people may be able to do it right away and answer the question. But I'm asking you, how do we figure this out? Okay, how do we figure this out systematically? But before we can even go there, we have to first, understand what the question is asking, right? So the question is asking, essentially, how many subsets are there relative to the set of ABC as a set? That's basically what it's asking. Okay, how many subsets can you generate out of the set of ABC? Wrong, and okay, so let me say that one more time. Wrong, right. Wrong. And right. That is correct. There we go. It is 8, okay, because it is 2 raised to the power of the set from which you want to create all your subsets. Now, how do we know that? Exactly. So Mohammed is asking a very good question. How do we figure this out? Well, okay. So the way to figure this out is actually deceptively simple, because for each element inside here, okay. So this particular set may have more things, but for each item in here, that element is either absent or present within any subset of this particular set. So we are now talking about binary stuff, right? So A can either be absent or present, B can be absent or present, C can be absent or present. So each time we have absent versus present, we have 2 choices. And the first element, okay, I shouldn't say the first, but for each element in the set of ABC, each one can either be absent or present, which means 2 choices. So you have to raise 2 to the power of the number of elements in the set, because each one, whether it's present or not, does not affect the presence or the absence of another element. That's why it is 8, because it is 2 raised to the power of 3, which is the number of elements. So I can now also give you a more general observation. So instead of using a very specific set here, if I just say, okay, let's pick one particular set that I call A over here. So the answer to this question is going to be 2 raised to the power of the number of elements in A. There we go. And the reason why it is not 2 raised to the power of the cardinality of A minus 1 is because we're using subset of instead of proper subset of. Because if we use proper subset of, then A cannot be a proper subset of itself, which means we have to subtract 1 from 2 to the power of the cardinality of A if this is not subset of, and instead it is proper subset of. So there we go. All right, cool. So you guys are already really kind of understanding the concept. Now, how can I tell that you guys are understanding the concept? I can't even see your face. I mean, you guys can be frowning profusely, and just having that troubled look is like that. And I cannot tell, right? Because, I'm not, looking at your webcam. You can turn it on, but I really cannot be looking at all the faces and look at the text channel and look at my own screen all at the same time. The reason why I can get that some of you at least are getting the concept because you were able to apply what we have talked about so far to figure this particular problem out. Okay, so if you can do that, that is a sign that tells me that not only are you understanding the notation, but you are connecting the concepts in order to solve this problem. So that's basically how I grade, how I do my exam as well, is I would ask questions, where you have to use what you have learned in class, all the definitions, all the concepts, all the symbols and whatnot, but you're going to be using those to solve a problem. So, the ability to solve the problem, is basically implying that you understand the concepts to the point where you can apply those concepts in a dynamic way to solve a problem. Now, the term dynamic in this case is important because it means that you might be solving a problem where you have not seen it in lecture at all. And I can almost guarantee you that you would have some questions in that particular format. So it requires you to basically apply all the things that you have learned, but not in a canned fashion. So you're not just following a sequence of steps that I have already done in class. You basically have to figure out, how does this connect to this one, and then this connects to this one, and then eventually I'm going to solve the problem. So just kind of keep that in mind because, that's how I'm going to ask questions in the exams. All right. So we are running out of time. I'm going to finish up reading the text channel, and then we are good for today. All right, 2 to the power of the cardinality. Each element is either present or absent. I would use the word combination very carefully because we do talk about combinations later on when we talk about combinatorics. So I'm just gonna be careful with that word. Each element is either absent or present. That is correct. Yep. Alrighty. So I think we are good here. The 7th set. Oh, okay, I see. So A, B, C, A, C, A. Oh, okay, I see. Okay, so I have been missing a little bit of a traffic when I was talking. So A, B, C, A, B, A, C, B, C, A, B, C, empty. So those are the sets. And Luke said, was wondering about the 7th set, which is the empty set, or is it? Yeah. So I think he's referring to the empty set. So the empty set is a subset. Yeah. So the empty set is a subset because in that case, all elements are absent. And earlier, we just talked about how the empty set is a subset of every set, right? So that's why the empty set is guaranteed to be in the set of subsets. Yeah. So there we go. And that's about it. Okay. So okay, I know we are going over time, but if you really want to kind of get a handle on these things, try to write a program to generate all the subsets of something. Okay, so don't go all the way out to but what can be elements? So just think about the elements of the numbers, numerical values of 0, 1, 2, and 3. Okay, and I'm asking you to write a program to generate all the subsets of a set where the elements are 0, 1, 2, and 3. And you can use whatever you need. Okay, write it in C, C++, JavaScript, or whatever. On what is it? Wednesday, that's right. So on Wednesday, I can show you, the JavaScript code that I would write, and for those of you who say, but I don't want to learn JavaScript, I want you to present your solution in C and C++, I can do that too. So we can take a look at that on Wednesday. And we are really ready to do the assignment, but I'm not going to assign it because some people have signed off already. So I will officially assign that assignment on Wednesday, but I will open it already today. It will be due next Wednesday. So you have like 9 days to work on it. Plenty of time. But for the rest of the class, people who have signed off already, they can start on Wednesday and they still have a week to work on it. All right, cool. And I'm just trying to catch up with the text channel. Alright, so it doesn't look like there are anything for me to answer in an interactive mode. So I'm going to stop the live stream and then I'm just going to finish reading everything in the text channel and see you all on Wednesday. So don't forget to kind of read ahead and review the concepts that we have already introduced. Keep nagging. Yep, there you go. Alrighty, see you guys on Wednesday.